Hello students, this is Uma Mishra. Now I have already posted 3 videos on capacitors, and in continuation with the same topic, today I will be dealing with the dielectrics, their behavior in presence of external electric field, and the capacitance of a parallel plate capacitor with a dielectric and a conducting slab in between. So let's begin the lecture. Now as you can see, I have already written over here. Now dielectrics are basically insulators since they don't have free charges. And they are of two types, the nonpolar and the polar dielectrics. The nonpolar dielectrics are usually monoatomic or combination of similar atoms like oxygen, hydrogen, even paper, mica, they are nonpolar. Whereas the polar dielectrics, they are polyatomic, a combination of different type of atoms, for example, water, HCl. Now let us come to the shape. If you view a non-polar dielectric atom, it is totally spherical in shape as the center of mass of positive and negative charge overlap. Their dipole moment is 0. But for the polar dielectrics, the shape is slightly ellipsoidal. The center of mass of positive and negative charge are separated, so their individual dipole moment is not 0. So in absence of electric field, the non-polar dielectric atoms appear in this manner, their dipole moment being 0. And for the polar dielectrics, the individual dipole moments are not 0, but the molecules are so oriented randomly that the resultant dipole moment is 0. That means whether it's a polar dielectric or a non-polar dielectric, in absence of electric field, the dipole moment remains 0. In presence of electric field, the non-polar dielectric atoms get slightly stretched out. The center of mass of positive and negative charge separate. That means a dipole moment is induced. And for the polar dielectrics, the molecules align themselves in the direction of the field and the resultant dipole moment is no longer 0. So both have induced dipole moment now. Hence we say that the dipole moment is induced in the dielectric in presence of electric field, and the phenomena of stretching of atoms of the dielectric and aligning in the field direction is called polarization. So we are going to learn few new terms over here. One is the polarization vector. Now induced dipole moment per unit volume is called the polarization vector. We express the polarization vector by a capital P, and it is the induced dipole moment per unit volume. So I have written their magnitudes. The induced dipole moment is the product of the induced charge and their separation, and so we can see that the polarization vector magnitude wise is nothing but equal to the surface charge density of the induced charge. Now look, we have placed a dielectric slab in the external electric field. And we have learned just now that in presence of external electric field, there is an induced dipole moment in each atom. So this is how the atoms appear. And they are bound charges, they are not free. But the positive charge of this atom is very close to the negative charge of the neighboring atom. The positive charge of this atom is again very close to the negative charge of this atom. So they neutralize each other's effect. And for us, this dielectric behaves as if there is negative charge at one end and positive charge at the other end. So an internal field is set up which opposes the external field. And this electric field is called the electric field due to polarization. So the field within the dielectric is the difference of the external field and the electric field due to polarization. And definitely the magnitude of the field in the dielectric is less than the external field, and its direction is same as the external field. Now the direction of the polarization vector, if we imagine a unit vector in the normal direction, outward normal direction, with respect to this we can say what is the direction of the polarization vector. The polarization vector P is along the unit vector normal, I have written as n, at the right surface, and it is opposite to the normal vector at the left surface, because this is a unit vector along the outward normal to the surface. So we can write the surface charge density of the induced charges as the polarization vector and dot the normal unit vector. Now if I consider the field within the dielectric in the vector form, we can express it as the vector sum of the external field and the field due to polarization. So we can see that EM, the magnitude EM, is equal to, we know that the external field is equal to sigma by epsilon naught. We had learned that in the first lecture, that the electric field within the dielectric can be written as sigma by epsilon naught. So this is sigma by epsilon naught, and the induced the field due to polarization which opposes the external field can be expressed as the ratio of the induced surface charge density by epsilon naught. So you have in the vector form, again I have taken it, and I can express this as sigma minus P dot n by epsilon naught, because we have already written sigma I as P dot n, and hence the surface charge density can be expressed in this form. And this vector, which is the sum of the polarization vector and the product of the field within the medium and epsilon naught, is called the displacement vector. So two new terms we have learned, one is the polarization vector and other is the electric displacement vector. And all these three vectors, the electric field within the medium, the polarization vector and the electric displacement vector, they all are in the same direction and parallel to each other. Actually, when we are talking these things in case of vacuum or air, the electric field between the parallel plate capacitor is related only to the free charge density sigma. But in presence of dielectric medium, the electric displacement vector D, it is directly related to the free charge density. We also express the polarization vector for a linear isotropic dielectric as the product of electrical susceptibility and the field within the medium. This is the electrical susceptibility of the dielectric. Now this is how the dielectrics behave in presence of electric field. They get polarized, then an induced dipole moment is set up, and the charges are bound charges. However, if you place a conductor in an external electric field, there the charges are free. So as soon as you place it in the external electric field, the free charges continue to move opposite to the field, the electrons in this case. They continue to move opposite to the field till the internal field and the external field become equal. And once they are equal, the resultant field inside the conducting slab becomes 0. So now let us see what is the capacitance of a parallel plate capacitor with a dielectric slab in between. I have taken a parallel plate capacitor. I have taken the cross section area of the plate as A, then the separation between the plates as D, and T is the thickness of the dielectric slab, E is the electric field between the plates of the capacitor, and the net electric field within the dielectric, as we have seen, is the difference of the external field and the electric field due to polarization. And in one of my last lectures, I had written the definition of the dielectric constant K, and one of the definitions was it is the ratio of the external field, that is in vacuum, to the field in the medium. And here we can express the field in the medium as E by K. And to find the capacitance, we know that Q is equal to CV. So to find the capacitance, we need the potential difference between the plates. And now the potential difference between the plates is not same everywhere. It will be different for this T thickness, and it will be different for the remaining thickness, which is D minus T. Outside the dielectric, where the thickness is D minus T, only one electric field acts, which is E. Within the dielectric, where the thickness is T, the field is EM. So, the potential difference between the plates outside the dielectric, I have written as E1, it is E into D minus T. And the potential difference within the dielectric V2, this is the product of EM and T. So, the total potential difference will be the sum. I have added both of them, EMT plus E D minus T. And then I have solved, I have substituted for EM as E by K into T, and then I have solved, and finally I have arrived at the expression Cm is equal to Q divided by V. I have substituted the value of V from here, and then we see that the expression is A epsilon naught by D minus T into 1 minus 1 by K. For air, for vacuum, the expression for C, it was equal to A epsilon naught by D, and here it is A epsilon naught by D minus this quantity, and capacitance is always positive, we know that. So, obviously the capacity increases when a dielectric slab is introduced between the plates. If the thickness of the slab is equal to the separation of the plates between the plates, then this capacity will be equal to A epsilon naught by D into K. Similarly, if we place a conducting slab in between the plates of the parallel plate capacitor, I have taken the same dimensions. A is the plate cross section area, D is the separation between the plates, T is the thickness of the slab, and we know that the field inside the conducting slab is 0. So, there is no potential difference over here, and the potential difference for the remaining thickness, which is D minus T, would be E into D minus T. I have substituted the value of E, and then again when you substitute in the formula the capacitance in the presence of conducting slab Q by V, substitute for V, and you get it as A epsilon naught by D minus T. So, once again we see that the capacity has increased even if a conductor is introduced between the plates of the capacitor. And if D is equal to T, then the capacitance becomes infinite. So, goodbye for this time, and we will continue in the next lecture hereby.